We saw that a dependent system in 3 variables has a line of solutions, except in the really awful case where it's all the same plane. But that's not going to happen very often. In this case, we can say what the solutions are instead of just saying infinitely many solutions. And there are several ways to do this. But one simple way is to just describe an ordered triple where one of the variables is left plain, and then the other 2 variables are described in terms of that variable. So only one variable will appear in the triple that we end up with. Now, we can choose any variable that we like. What we will do is choose whatever variable makes our math easiest. So let's see an example now of a system where we have 3 variables, 3 equations, and it turns out that it's dependent. This is the same example system we saw in the last video. We're going to try to solve this system now and see what happens. So let's see. Looking at these equations, it looks like y is going to be by far the easiest to eliminate. In fact, if I decide to eliminate y, I can eliminate it first by just adding together equations 1 and 2 without multiplying by anything, because I see that these y's have opposite coefficients out of the box. So I'm going to take equation 1, 4x minus y minus 3z equals negative 3. Line up equation 2 underneath it. 2x plus y minus z equals 1. And add those together to get 6x minus 4z equals negative 2. In order to make my future self's life easier, I'm going to go ahead and put this in standard form. I see those numbers all have a common factor of 2. I'm going to divide by that, and I'll have 3x minus 2z equals negative 1. I'll call this equation 4. Okay, so I'm still eliminating y. Now I need to do something with equation 3. It looks like if I multiply equation 1 by 4, I'll be able to cancel out that y term. So equation 1 times 4 plus equation 3. I'm going to multiply 4 times equation 1. Multiplying that out, I'll get 16x minus 4y minus 12z equals negative 12. Then I'll write equation 3 underneath that. 5x plus 4y minus 2z equals 5. Adding those together, I'll get 21x minus 14z equals negative 7. And then noticing that all of those coefficients have a common factor of 7, I'll divide through by that, and I'll have 3x minus 2z equals negative 1. I'll call that equation 5. And I notice that equations 4 and 5 are the same. And that's what tells me I have a dependent system. So this system now, it's actually only one equation, but it contains the variables x and z. We can choose either one to write our eventual line in terms of. I'm going to choose x because I like having an x, right? Writing everything in terms of x feels nice. So I've got 3x minus 2z equals -1. I'll solve that for z. So -2z equals -3x minus 1. Divide by -2. Z equals 3/2 x plus 1/2. There I have my z in terms of x. And this is equation 4, just solved for z. Now, to get y in terms of x, I need to go back to one of my original equations and plug this in for z. So I'm going to look at my original equations. I like using equation 2 to find y because that has y all by itself. So I'm going to choose that. I'm going to plug this equation 4 into equation 2. And that'll give me 2x, I want to keep x's, that's fine, plus y minus, now my z is equal to 3/2 x plus 1/2. And according to equation 2, that's all equal to 1. So let's see. 2x plus y minus 3/2 x minus 1/2 equals 1. So collecting all my like terms, 1/2 x plus y minus 1/2 is 1. And then getting rid of everything that's not y on the left, I have that y is -1/2 x plus 3/2. So my solution set is all the points of the form x can be anything that it wants, and then y is -1/2 x plus 3/2, and z is 3/2 x plus 1/2. So x can be any number, y and z depend on x. That describes a line in space.